we're going through the third type of distribution problem. This is where we distribute R distinct objects to n identical boxes. So in previous videos, we were distributing to distinct boxes, and that made it easier because we can do a bijection to arrange them in a linear order. But now, because they are identical boxes, we cannot do so. And also, if we just divide by n factorial, it is not correct because without the bijection, we are not putting the boxes into the objects. We are trying to distribute the objects to the boxes, and it's only because previously we were doing distinct we get the bijection. Without it, we cannot just divide by n factorial, and that will be wrong. So they come out with other ways to do so, and one way is just to define this number over here. And so this number is called the Stirling number of the second kind, and it is defined to be the number of ways to distribute R distinct objects into n distinct identical boxes such that no box is empty. So this is an important condition, no box is empty, so that we can get a very nice recurrence relation that we'll go into now. So before that, let's set up some initial conditions. One will be that S00, which is distributing 0 objects into 0 boxes, that is defined to be 1 by definition. Because you can think of it as you're distributing nothing into nothing, and that is like a always true statement, so it's 1. Also, if R is greater than n, so R is some positive integer and n is 0, then that will be no ways. And also, if n is greater than R, then there will also be 0 because there will be empty boxes. So if it's R is a positive integer and n is 0, it's 0. If R is 0 and n is a positive integer, it is also 0. But if both are 0, it is 1. And this so means that you can only distribute the objects such that no box is empty when R is greater than n, both larger than or equals to 1. And also, if n is ever larger than R, when both are larger than 1, then it is 0. And then if R is a positive integer and n is 1, then there's only one way, because you can only put all these distinct objects into one box. And if there are R boxes, then SRR is 1, because no box can be empty, so you need to put all the distinct objects into every box. So now let's go on to this important identity, this recurrence relation. SRn equals to SR minus 1 comma n minus 1 plus n times SR minus 1 comma n. So let's prove this with a combinatorics proof. In our first case, let's just say one of the distinct objects A1 is alone. Then the number of ways to distribute will be just the remaining R minus 1 objects distributed among the n minus 1 identical boxes. So it's SR minus 1 comma n minus 1. And in case 2, A1 is not alone. So if it's A1 is not alone, we rather arrange what is remaining first. And that is the R minus 1 distributed among n boxes. Then A1, because once you distribute them, and since every object is distinct, this allows the boxes to become distinct. And so A1 now has n choices to choose from. And adding them up gives you this identity. With this identity, it allows us to use a computer to calculate what we want easier, because if we do not, then the manual computation will take quite a while. So here is a code that I provided that allows you to run this Stirling's number of the second kind, and you will see, and we'll go through why it works based on the logic that we have run through in this page. So let's see. Well, we first define our Stirling's number as SRN. Now, if R is less than 0, we return 0. Of course, because if it's any negative, then there's no distribution. If N is less than 0, we return 1. 0, I mean, sorry. If both R and N is 0, then as we define, it will return 1. If R is not equals to 0 and R equals to N, which just means that N equals to R, then we'll return 1, because as we said, we have to put all the objects into every single box, so we can only put 1 each. And then if R is less than N, we return 0, and this fulfills whatever we have said earlier over here. And so now we typed in this recurrence relation after covering all the cases, where N times N minus R minus 1 N plus R minus 1 comma N minus 1 will be returned. And so we run it, and we can just see that S11 already, let's say we run it, it should be 1. As we define, S00 should be 1. Now, before we move on to seeing more complicated examples, that we also do not want to always we sometimes need to manually compute, and sometimes certain conditions allows us to compute it easier. Well, let's see. So one more identity will be SR2, where that means there's 2 boxes only. Then there's this closed form formula where it's 2 to the power R minus 1 minus 1. Reason for that? Well, just put one of the distinct objects into one of the box. Then this box now has A1 and the other box is empty. So now these 2 boxes are distinct, and so every other R minus 1 object has 2 choices to make, either go into this box or go into this box. And so 2 to the power R minus 1 is the number of ways. But we cannot have all the objects go into A1, because this will leave one of the box empty. And so that sole case must be minus off. And therefore you result in 2 to the power R minus 1 minus 1. This allows us to compute S42 easily, because S242 is just 2 to the power 3 minus 1, which is 7. And we can verify that that is true with our code. So we just type S42. This will run and gives us 7. We can again check that S62, which is 2 to the power 5 minus 1, is 31. So S62 is 31. As seen, we can see that this code obviously works because we run the thing recursively, and with our formula it verifies that it is true. I'll be sharing this code with you, and now let's move on to see some application of Stirling's number of the second kind. One application that I'll go through will be the partition of distinct elements. Take note, this is distinct elements, as later on we'll see the case for identical in a separate video. So let's say you got 5 elements. A 2 partition is denoted as when you split this 5 element subset into 2 parts. So 2 partition means 2 parts. 3 partition means 3 parts. So you can just see one partition means all 5 of them is in one box. As you can see, splitting them is just distributing these 5 distinct objects into how many boxes. And so the total number of partitions from 1 to R objects will be S R, N. So this just means the partition of n objects, and then it is just 1 to n, and it's the number of partitions from 1 to n total. So this is R, and so you first have a 1 partition, 2 partition, all the way. And that's basically it for Stirling's number of the second kind. I hope you have enjoyed the video. Please feel free to like, share and subscribe. And I'll catch you in the other videos. Thank you.